Hi there, my name is Pranav, and today we're going to be learning about black holes. And the last lesson, I said that we're going to be talking about Hawking radiation. And just know that in this lesson, I'm just once again going to give like a brief introduction of what it is. But to dive into it, it is more complicated than you think. So I'm just going to go over the brief details about Hawking radiation, basically. Okay, so to start off with, um, where did it originate from? Now, the person who discovered this radiation was called Stephen Hawking. As you can see, Hawking radiation, Stephen Hawking. You see the connection? Okay. So basically, this person was a cosmologist and like an astrophysicist who basically discovered the Hawking radiation, and that's why he's actually very popular. He's like a I guess idol in like the science field, mostly like in the quantum field section. Now, yeah, that's exactly why he's important. Um, Now, yeah, about the Hawking radiation, basically what it is it's the thermal radiation predicted to spontaneously be emitted by black holes. Now, this concept can be used to detect how long the black holes can live. How long can they maintain their form or structure, which is a good thing. Now, how do you find this? Now, Stephen Hawking, um, he had he had to reference to multiple equations, and it's this is all like mathematical. It's it's very hard by also by itself because coming up with equations and proving them, it's really a difficult thing. But um, with Stephen Hawking's dedication and lifetime work, he has made this equation, which is s equals to um, the numerator like pi a k c cube over 2hg capital G. Now the s here, it's the entropy of a black hole basically, okay? And the a here is the physical properties of a black hole, like the area. Now yes, I am going to be talking more about these like variables because they themselves are like a big topic. Okay, so I'll probably like I'll see how I'm gonna be like making the videos on this variables, but just know that this is the equation. Just know that what what the variable represents. Okay, so S is the thermodynamic quantities, such as the entropy of the black holes. A is the physical properties of a black hole, the area. K is the Boltzmann constant. C is the speed of light. H is Planck's constant, and G is Newton's universal gravitation constant. Now, um, I'm not going to be telling you some of these constants. These ones you can search on the internet, and I'm going to be asking you as part of the worksheet to find these constants. Okay? I'm not going to ask you what it is. Just tell me the numerical value and the units. Okay? That's going to be like part of the one of like the question. So now, the problem about this Hawking radiation, is that it has yet to be observed. Scientists have not observed it, have not been able to find it. Now, I've like searched through many articles, and I found that apparently Stephen Hawking has not like received a Nobel Prize, and this is the reason. It's because the Hawking radiation, no one has ever observed it. Yes, I know he has this all like complicated math equation, but just because you have like the equation doesn't mean it's like exactly correct. It's like it's kind of difficult. Like this is dwelling in like the quantum field theory, and it gets really like abstract, and equations themselves are not exactly the most valid um, like way to confirm. Like I'll give you an example. Okay, so you know how for when we like the SI unit for time, we use seconds, right? And 1 second is basically the word the amount of time you take to pronounce the word Mississippi, which is about 1 second. Okay, and some fun facts, and um, okay, and we like we have like 1 day, 2 days, like 365 days, such as like a year. Basically, how do we measure a day? Now we measure a day by the amount of time it takes to like for the um, like how can I explain this? Okay, so um, early morning the sun's rising, and it's rising and it comes up, and then at some point of the night it goes down. So it's basically the measurement of like like at each time the sun is at some particular position, right? So we use the um, yeah, we use 24 hours. Like we call one day as to be 24 hours, and that's the amount of time the sun like takes to move around. Not move around. What's the word? Correct. It's the it's like our day cycle. It's like the time the sun takes to come to a particular position. Sorry, like within our like view. Now, depending on the place where you are on Earth, the time is works different. Like for example, here in Thailand, sorry. Oh, hold on. It's about 5. Okay, it's about 5 p.m. Now for the U.S. time, I think it's like 20. Sorry, 12 hours delayed. I mean, like 12 hours back. So it's like about 5 a.m. for them. Whereas like for us, when it's about p.m. for them, it's a.m. And there's when they experience nighttime, we experience daytime. It kind of works at that. Okay. So now, um, one thing that um, yeah, yeah. Okay. Now the point I like trying to say is that the you know how like we have revolutions, right? Like for us, it takes 1 year for the Earth to revolve fully. Now, mm, okay. Now, for like the planet next to us, Mars, Jupiter, and all those planets, the time works really different. For them, um, their daytime is more longer. Um, it's- like the closer you are to the sun, the faster the day cycle is. Okay, the further you are, the longer it takes for like the day cycle. Like it's gonna be like a long, long night, long, long morning. It's gonna be like that. Um, and like the closer you are to the sun, the more temperature there would be, and the further you are, the colder it would be. And for us, we're lucky to be in this, zone, like the Goldilocks zone, in which where we life can exist. It's like the perfect temperature we're being exposed to. Okay. Now, um, if you take the concept of time, basically it's time like the day cycle, right? The amount of time for them to revolve, and for the amount of time like the day occurs is different. It's like expanding. But now, is this limited to our galaxy or the entire universe? Now, it's kind of a little different. Like this is only within our solar system. outside our solar system, it works differently. For each like solar system, there's a different. It works entirely different. Like the day cycle, um, it can be. It's kind of difficult to explain, but like they have their own different time, like the amount of time it takes for like a day to occur. It's not exactly like constant within all solar systems. Like it works very differently. Yeah, it's kind of difficult to explain, really. But that's the thing, That's like, yeah, it's like something that's abstract. Like we can like prove it by equations and that, but then obviously within that equation there's like some kind of like exception. Now, okay, um, what was I gonna say here? Okay, so the yeah, okay, this is referencing to like the black holes, like lifetime, I guess. Basically like the Hawking radiation, right? Um, this is like this phenomenon, like it having like entropy and a loss of energy, and it emitting radiation over long time scales. It's like labeled as Hawking radiation. Now, the loss of energy here is very important. Um, like, sorry, the and we can use entropy like as a way to like explain the lifetime. But okay, I'm gonna talk about this next like lesson because this is a little like difficult for me to explain as well. Um, for this video, I guess I'm just gonna ask you like some minor questions, insignificant ones, because we're not ready for the tougher ones. So sorry for the long video. Okay, stop recording. Okay, goodbye.